few months ago, someone left a comment on my YouTube channel saying, "What about space-based solar power?" And I had said anything that works would be a good addition to the climate solution portfolio. But now the Europeans, especially UK as well, are going into spending a lot of money on testing some of the concepts. Usually space-based solar power was almost like science fiction till a few years ago. So you would imagine a satellite that's flying around and is able to collect solar power in space. You don't have the day-night issue, dust issue, cloud issue, so you could presumably harvest solar energy 24 hours a day and then beam it down. This beaming down is not as easy as one would imagine, so we'll look at some of those things. And there's a discussion in the last week's edition of the journal Science talking about whether the space-based solar power concept is becoming a reality or getting close to becoming a reality. So I'll go through some infographics from various sources along with some technical issues and a couple of concepts of satellites for space-based solar power, often referred to as SBSP. So this is from greenmatch.co.uk. UK has put billions of dollars in trying to convert to test some of the concepts. So what is space-based solar power? Obviously, space-based solar power collects the sun's energy in space and wirelessly transmits it back to Earth. You don't imagine cables hanging down like the power grids work these days from the power plants, but this is wireless transmission. So giant mirrors are installed in space to collect solar energy from the sun. Solar panels in space convert solar energy into electricity. So there is the concept of a satellite. And then somehow you would beam it down wirelessly like an energy converter, maybe a laser, microwave, something like this, to a power structure that is on power station that's on the ground, and then the energy is, that is beamed through the laser is converted back into electricity. Sounds very easy, but remember that beaming down gigawatts of energy, one has to be very careful about who may get fried along the way, birds, people, etc. The current global energy consumption trends from the same website: 160,000 terawatt hours of energy consumed annually. This year may be already a little bit off by one, but the numbers are in the right ballpark. Over 60% of this energy is generated from fossil fuels, which is why we are trying to talk about space-based solar power and other renewables in the first place. Obviously, CO2 emissions are accelerating despite the 25 years of negotiations, and the world population is expected to reach 9.7 billion in 2050 if we continue to go with the fertility rates right now. But we know that this could change a lot if the drops in fertility and reproduction continue the way they have in many countries, most notably in China, and India also has reached its peak fertility rates already. So without going into that further, a 50% increase in energy consumption is predicted for 2050. So why space-based solar power? It's 40 times more energy generated annually than solar panels on Earth, just because of the day-night issue and cloud-free days and so on. Almost 0% hazard waste to our environment. This sounds nice, but we don't want to increase space debris too much either, so one has to worry about it. No greenhouse gas emissions compared to oil, gas, ethanol, and coal plants, which is of course very attractive. 24 sunlight hours a day, 99% of the year, meaning continuous power generation. Are we not there yet? Well, space-based power, solar power requires high investments and research before it's ready for use, and concepts are being tested for the idea of generating electricity, transmitting it wirelessly, and converting it back into electricity, usable electricity, and scalability of 1 megawatt to many hundreds of megawatts and so on. High development costs and high transport costs to space, high damage risk to the solar panels from space debris and radiation. Technological demands are very expensive at this point. High risk of wasted energy during transport back to Earth. So you can imagine the engineering of launching things to space have to drop in price by a lot, like what Starlink's Tesla has done. The efficiency of energy transmission has to be upward of 70 to 90%. That's very critical, and of course safety issues as well, and the technological demands as well. And the research to reduce costs goes on, especially in Europe. But here are the projects and plans by global players. A few key players are already taking steps to make space-based solar power a reality. China shows up on top here, and Japan and a couple of more countries in the next slide. Plans to launch small solar satellites into the stratosphere in 2021 that can harness energy in space. Now, it didn't happen, pandemic and so on. By 2030, China plans to generate 1 megawatt of energy. Doesn't sound like a lot, but as a concept that'll be amazing. By 2050, China plans to have a commercially viable space-based solar plant. China is already building space station and doing all kinds of experiments. Doesn't include this yet, but I'm sure it will. 100 million partnership between Northrop Grumman and US Air Force Research Laboratory to advance technology for space-based solar power. 17.5 million Space Solar Power Initiative aims to develop technology to enable SBSP systems to generate electricity at a lower cost. This is all in the US. Reusable launch systems are being researched to lower the cost of launching and assembling of SBSP in space. SpaceX is working on reusable launch vehicles that can be used for space transport. So that's again transport. That's again our friend Elon Musk. Development of the SPS Alpha Mark II concept uses new technologies and has advanced economic feasibility of a SBSP project. In Japan, Japanese researchers successfully transmitted electric power wirelessly using microwave, which is an advancement towards SBSP technology, of course. Made space-based solar system part of its future space exploration vision. Okay, so coming to the Science article, which points out how the efficiencies are improving, launch costs are coming down, the wireless transmission technologies are being tested and scaled up, or testing for scaling up, etc. So the infomercial from Science article goes this way. Here comes the sun. The plummeting cost of space launches and electronics may make space solar power viable. All designs need photovoltaic cells, sometimes fed by mirrors and microwave transmitters, to beam down energy, and all will be kilometers wide, requiring assembly in orbit. Below is a design concept from the International Electric Company. So the panels have to be designed so that they're always pointing at the sun, or they have mirrors which can take the sunlight and point it onto the panel, solar panel. And of course those mirrors can be used for concentrating solar power as well. Okay, so here is Earth, here is sunlight coming in, and it's a 6 kilometer wide concept here with these components catching the light. Lightweight mirrors on either end deflect sunlight towards the central solar array. Satellite rotates to keep them pointing sunward. And secondly, making power, PV cells convert light to electricity, which is used to generate microwaves. Every time you convert, there is always an efficiency issue and loss issue, of course. Third, beam it down. Phased array of transmitters focuses gigawatt power beam anywhere on Earth in line of sight. Obviously, this sending gigawatts of power through the atmosphere to Earth needs enormous amount of care and safety. Receiving station here at 4 kilometers wide array of antennas on land or offshore converts microwaves to electricity for the power grid. Offshore would be easier in terms of beaming down the energy, but then you have to worry about transmitting from offshore on to land as well. Other infographic from Space-Based Solar Power European Space Agency. Incident solar radiation in orbit, the intensity of sunlight is much higher than intensity at Earth's surface. This is obvious because of all the atmospheric interferences, including clouds, dust, water vapor, and so on. Sunlight, sunlight capture and energy regulation. Sunlight is converted into a current, then prepared for radio frequency beaming to Earth, the moon, or another planetary surface. So you can imagine that this technique can be used to also colonize moon and get power from these SPSPs to the moon's surface. Power beaming. Energy is sent down to Earth using phased arrays, laser emitters, or other wireless technologies. The energy beam must be accurate, reliable, and should retain as much of its power as possible as it travels through Earth's atmosphere. So energy loss, efficiency of transmission has to be very high priority as well in terms of improving research-based ideas and scaling them up. Beam capture and energy conversion. Energy beam is captured with photovoltaic cells or with an antenna that converts electromagnetic energy from the sun into electricity. Satellites can beam energy down to a single ground site or to several locations around a planetary object. Okay. Power transmission then requires further care. Systems that collect the space-based solar power on Earth must be safely and sustainably integrated into existing power grids. Power distribution is also vital in science, exploration, and colonization missions like the moon landing, moon colonies, moon camps, whatever you want to call it. Energy utilization, as well as having potential to aid Europe's goal of becoming carbon neutral by 2050, space-based solar power technologies could provide the flexibility and reliability required for science and exploration missions where other power sources are limited, for example, rover missions during lunar night. Okay, so you can imagine all these components here, which is all nice schematically speaking, but one has to really wait for the concepts to be tried and the key technology barriers have to be overcome, like the energy efficient transmission, safe transmission from space solar power to ground-based stations, power stations. This physics world provides a couple of concepts. Number one on their list is this one. Sorry, I flipped the order. Multi-rotary joints solar power satellites, MRSPS. This concept for space-based solar power builds on the original 1968 proposal devised by the US engineer Peter Glaser. So US considered space-based solar power in the 1970s during the oil crisis, but the costs were so prohibitive that it was never implemented. Known as the multi-rotary joint solar power satellite, it was invented in 2015 by Hu Xibin and others at the China Academy of Space Technology in Beijing. The 10,000-ton satellite, which is about 12 kilometers wide, would move in a geostationary orbit, so it's always pointing at China, for example, roughly 36,000 kilometers above the Earth, with sunlight collected by solar panels and converted into microwaves that are beamed to Earth by a central transmitter. To allow power to be transmitted continually to us, the photovoltaic panels can turn to face the sun relative to the central transmitter, which always faces Earth. So you have the solar cells tracking the sun and the transmitter always pointing towards the Earth. The solar panels and transmitters are connected by a singular rectangular scaffold. Unlike rival designs, the MRSPS concept does not rely on mirrors. So somehow the panels always have to track the sun, and this design doesn't include mirrors. Second on the physics world list is SPS Alpha. You can see it has multiple components, as we will see in a minute. In the SPS Alpha concept, invented by former NASA engineer John Mankins in the US, the main body of the satellite, the solar panels and transmitter, is fixed and always faces Earth. Stationed in a geostationary orbit, the 8,000-ton satellite consists of a disc-shaped array of modules that convert sunlight to electricity via photovoltaics and then transmit that energy as microwaves. Connected to this 1700 meter diameter array is a separate, larger dome-shaped array of mirrors which independently turn to reflect sunlight to the array depending on where the sun is positioned relative to Earth in geostationary orbit. So the mirrors are used here as concentrating solar power to shine onto the cells, and this can presumably increase the efficiency or at least increase the amount of sunlight that's always falling on the solar panels. Okay. Finally, this concept has multiple components. Sorry about the previous comment. Solar power satellite is here, wireless transmission is here, and there is a ground station with Rectenna, which is converting microwave into electricity. And there are, focusing in on this one, there are solar reflectors, so sunlight is coming in, power transmission is happening down this way, but solar panels and transmitters are together here, and this diameter here is 1700 meters. So this is the solar power satellite that is zoomed in, that is shown here, and then this structure is explained here. So the Cassiopeia proposal for space-based solar power developed by Ian Cash at the International Electric Company Limited in the UK envisages a satellite with a mass up to 2,000 tons sitting in a geosynchronous or elliptical orbit around Earth. Sunlight strikes two huge elliptical mirrors, which are shown here as LO disks, each up to 1700 meter in diameter, that lie at 45 degrees to a helical array of as many as 60,000 solar panels. So this is 60,000 solar panels which are receiving the reflected solar energy. These panels collect the sunlight and turn it into microwaves at specific frequency, which are then transmitted to a ground station on Earth roughly 5 kilometers in diameter. This station converts the microwaves into electricity for the grid. The advantage of the helical geometry is that the microwaves can be constantly directed towards the Earth without needing articulated joints, which often fail in space environments. Finally, the microwaves are instead steered via adjustments to the relative phases of the solid state dipole. So you can see that figure being shown here. So here is the array, and then these are the microwaves being steered via adjustments to the relative phase of the solid state dipoles. So the engineering aspects have been well thought out, and the concept is now moved much further along than just science fiction. Many concepts are being tried, substantial amount of funding has been made available, and everybody is thinking about geostationary orbits, obviously, because you want the solar power to come to you all the time, just like weather satellites pointing at your region to provide data for weather forecasting, disaster management, and other things. Okay, so that's just a short run through the space-based solar power concepts that I wanted to include here, since it's now getting closer to being a reality with so much funding and so many improvements in launch technologies, reduced cost of launching, efficiencies of transmission, efficiencies of the solar cells, and the structural constraints on the whole assembly of panels, mirrors, and microwave generators in the satellite assembly. Okay.